For most of the last century, cosmology rested on a reassuring assumption. The universe had a history that unfolded in an orderly sequence. First came the Big Bang, then darkness, then the first stars, then small galaxies. Those galaxies merged into larger ones, generation after generation, until structures like the Milky Way finally emerged billions of years later. The timeline was never arbitrary. It was built from decades of observations, computer simulations, and physical laws that seemed to reinforce one another. Gravity gathered matter, gas cooled, stars ignited, heavy elements accumulated. Complexity required time. That expectation shaped almost every modern model of galaxy formation. Then a new telescope opened its mirror. The James Webb Space Telescope was never intended to overthrow modern cosmology. Its purpose was far more practical. By observing infrared light that had traveled for more than 13 billion years, Webb would allow astronomers to examine galaxies that existed when the universe was still remarkably young. In effect, it would extend our vision deeper into cosmic history than any previous observatory. NASA science. Before Webb, many researchers expected to find primitive systems, small collections of stars, uneven clumps of gas, objects still struggling through the earliest stages of assembly. Instead, the first observing campaigns revealed something that immediately demanded careful scrutiny. Some of the earliest galaxies appeared brighter, larger, and more chemically evolved than many existing models had anticipated. Several candidates seemed to exist only a few 100 million years after the Big Bang, yet they displayed characteristics that suggested surprisingly rapid growth. That observation spread quickly through both the scientific community and the public. Headlines declared that cosmology might be broken. Others claimed the Big Bang itself had failed. Neither conclusion reflected what astronomers were actually saying. Science almost never advances through dramatic collapse. More often, it advances through uncomfortable measurements that refuse to disappear. The first question was deceptively simple. Were these galaxies truly as distant as they appeared? Initial estimates relied on photometric measurements. By comparing brightness through different filters, astronomers could estimate how much cosmic expansion had stretched a galaxy's light. It was an efficient method, but not a perfect one. Certain combinations of dust, gas emission, and unusual stellar populations can imitate the colors expected from much greater distances. Spectroscopy would decide. Instead of estimating distance indirectly, spectroscopy measures precise shifts in known atomic signatures. It is slower, more demanding, but considerably more reliable. When spectroscopic observations arrived, something important happened. Some celebrated candidates did not survive. A few galaxies initially believed to belong to the earliest epochs turned out to be much closer than expected. Their unusual colors had misled the original estimates. If the story had ended there, Webb would simply have reminded astronomers that extraordinary claims require stronger measurements. But the remaining confirmed galaxies created a different problem. Even after removing mistaken candidates, several distant galaxies remained unexpectedly luminous, unexpectedly mature, unexpectedly productive. The issue was never that galaxies existed early. Standard cosmology predicted they would. The issue was how quickly some appeared to build stars. Inside computer simulations based on the current lambda cold dark matter model, galaxies require time to collect gas, convert that gas into stars, recycle heavier elements through stellar evolution, and gradually assemble larger structures through mergers. Webb began finding systems that seemed to accomplish much of that process sooner than expected. Not impossibly soon, just early enough to become uncomfortable. That distinction matters, because astronomy is full of apparent crises that later dissolve under better measurements. Sometimes masses have been overestimated. Sometimes black holes brighten galaxies enough to make them appear more massive than they really are. Sometimes assumptions about stellar populations quietly influence every calculation built upon them. Arsiv. In other words, seeing a bright galaxy does not automatically reveal how much matter it truly contains. Brightness is only the beginning of the investigation. Suppose an early galaxy formed unusually large numbers of massive stars. Instead of following the stellar distribution commonly assumed today, massive stars produce enormous amounts of light while living only brief lives. A galaxy dominated by those stars could appear much heavier than it actually is. Or, perhaps, star formation in the young universe proceeded with remarkable efficiency under conditions unlike anything nearby today. Or, perhaps, active black holes contributed much more of the observed light than initially recognized. Each explanation preserves much of modern cosmology, while forcing astronomers to rethink the details of galaxy evolution. Notice what has happened. The question has already changed. We are no longer asking whether Webb discovered galaxies. We are asking whether we understand what those galaxies truly are. That difference transforms the entire investigation, because telescopes do not observe theories. They observe light. Everything else depends on interpretation, and interpretation becomes increasingly fragile the farther we look back through time. The earliest universe offers no opportunity for second chances. Every photon reaching Webb has crossed billions of years before entering its mirror. Those ancient signals are faint, distorted by expansion, and filtered through assumptions about how stars, dust, gas, and black holes behave under conditions we cannot reproduce on Earth. The farther we see, the more every hidden assumption begins to matter, which leads to a deeper possibility. Perhaps the greatest challenge posed by Webb is not that the universe evolved differently than expected. Perhaps it is revealing how dependent our confidence on models built from an era of cosmic history, much closer to home. The earliest galaxies are no longer simply distant objects. They have become tests of the framework we use to reconstruct the entire history of the universe. And the next layer of evidence makes that test considerably harder to ignore. One reason the first Webb images generated so much attention is that they seemed to challenge something deeper than galaxy formation. They challenged our intuition about time itself. If the universe is about 13.8 billion years old, then looking farther away is equivalent to looking farther into the past. Every additional billion light years strips away another chapter of cosmic history. Astronomers are not watching distant galaxies as they exist now. They are seeing them as they were when the light first began its journey. That means every unusually mature galaxy found at extreme distances compresses the amount of time available for its own formation. The arithmetic is simple. The physics is not. For decades, cosmologists have relied on increasingly sophisticated simulations to reconstruct how structure emerged after the Big Bang. Vast clouds of invisible dark matter collapsed under gravity, forming dense regions where ordinary matter accumulated. Gas cooled inside these halos. The first stars ignited. Those stars enriched the surroundings with heavier elements after exploding. New generations of stars were formed from that enriched material, while neighboring galaxies gradually merge into larger systems. The process resembles the growth of a city. A small settlement can become a metropolis, but roads, buildings, industries, and neighborhoods do not appear simultaneously. Growth depends on resources, infrastructure, and time. Speeding up one part of the process usually creates pressure somewhere else. Galaxies face similar constraints. Stars cannot form unless enough cold gas has accumulated. Heavy elements cannot appear until previous generations of stars have already lived and died. Large galaxies generally require repeated mergers or exceptionally efficient star formation. The difficulty raised by some Webb observations is not that these processes happened. It is how quickly they appear to have happened together. Researchers immediately began testing whether the apparent tension reflected weaknesses in the observations or weaknesses in the assumptions used to interpret them. One possibility centered on stellar populations. Most estimates of a galaxy's mass begin by asking how much light different kinds of stars should produce. Those calculations depend on what astronomers call the initial mass function, a statistical description of how many small stars form compared with large ones. Nearby galaxies seem to follow a fairly consistent pattern. But the early universe was not nearby. It contained almost no heavy elements. Gas clouds behaved differently. Temperatures were higher. Conditions may have favored the formation of much larger stars than those commonly seen today. If that happened, a young galaxy could radiate extraordinary amounts of light without containing as much total mass as first estimated. The apparent crisis would shrink considerably. Another possibility involves dust. Dust sounds insignificant, yet it profoundly affects astronomical measurements. Tiny grains absorb and scatter light while re-radiating energy at different wavelengths. Misjudging the amount or composition of dust inside a distant galaxy can alter estimates of age, star formation rate, and even stellar mass. Then there are active galactic nuclei. Supermassive black holes surrounded by rapidly falling matter release enormous amounts of radiation. In some cases, a brilliant central black hole can make an entire galaxy appear far more luminous than its stars alone would suggest. Separating those contributions is difficult when the object itself is only a faint collection of ancient light photons. Every improvement in the data reduces one uncertainty while exposing another. That pattern is familiar throughout the history of astronomy. The first measurements rarely settle a question. They refine it. As more Webb observations accumulated, astronomers noticed something encouraging. The original tension remained, but its magnitude appeared smaller than many early headlines suggested. Better spectroscopy, improved modeling, and larger observational samples reduced several of the most dramatic discrepancies. Yet they did not eliminate them entirely. Some galaxies still seem capable of converting gas into stars with remarkable efficiency. Some still are unexpectedly massive for their age. Some continue to occupy regions of parameter space that earlier simulations rarely produced. Instead of asking whether cosmology has failed, many researchers began asking a subtler question. Are our simulations missing important astrophysical processes? Computer models are not the universe. They are attempts to approximate it. Every simulation balances physical realism against computational limits. Star formation occurs on scales vastly smaller than an entire galaxy, forcing modelers to represent complicated processes through simplified prescriptions. Stellar winds, supernova explosions, magnetic fields, turbulence, radiation, and black hole feedback all interact across enormous ranges of scale. Small adjustments in those prescriptions can produce surprisingly different galaxies billions of years later. That possibility may sound disappointing. It is not. It reflects one of science's greatest strengths. A successful theory is not protected from inconvenient observations. It is forced to explain them. The lambda cold dark matter model has survived countless tests because it successfully predicts the large-scale expansion of the universe, the distribution of galaxies across immense distances, patterns in the cosmic microwave background, and many aspects of gravitational structure formation. Weaknesses in one area do not automatically invalidate its successes elsewhere, but neither can successful predictions excuse persistent anomalies. Every enduring scientific framework carries hidden assumptions. Most remain invisible until observations begin pressing against their limits. Webb has become extraordinarily effective at applying that pressure, not by announcing that everything we believed was wrong, by revealing where certainty becomes conditional. And there is another reason these early galaxies matter. They are not isolated puzzles. Their existence connects directly to another question that has quietly shaped cosmology for decades. How quickly did the universe emerge from its first great darkness? The answer depends not only on when the earliest galaxies formed, but on what those galaxies were capable of doing to the universe around them. That next chapter shifts the investigation from individual galaxies to one of the largest transformations in cosmic history. Long before there were planets, oceans, or living cells, the universe passed through an era that left almost no visible trace. Astronomers call it the Cosmic Dark Ages. The name sounds dramatic, but it describes something remarkably literal. After the universe cooled enough for electrons and protons to combine into neutral hydrogen, space became largely transparent. The brilliant glow of the early plasma faded into what we now observe as the cosmic microwave background. Yet no stars had formed to replace that light. For millions of years, the universe contained matter, gravity, and expanding space. It lacked illumination. Gravity continued its work in silence. Tiny irregularities, left behind by the Big Bang, slowly attracted more matter. Invisible halos of dark matter grew denser. Ordinary gas drifted toward them. Somewhere inside those halos, the first stars finally ignited. Those first stars were unlike the ones surrounding us today. Because the early universe contained almost no heavy elements, the gas cooled less efficiently. Many theoretical models suggest that the first generation of stars more massive than typical stars forming in the present-day universe. They would have burned through their nuclear fuel rapidly, lived only a few million years, and ended their lives in violent explosions that seeded space with the first heavy elements. Whether every detail of that picture is correct remains an active area of research. But the broad sequence is supported by multiple independent lines of evidence. Those first stars did more than produce light. They transformed the universe itself. Neutral hydrogen, which had filled intergalactic space since the end of the Dark Ages, absorbs ultraviolet radiation efficiently. As the earliest stars and galaxies emitted energetic photons, they began stripping electrons away from hydrogen atoms once again. Gradually, bubbles of ionized gas expanded around young galaxies. Over hundreds of millions of years, those bubbles overlapped. The universe underwent what astronomers call, it was not a single event. It was a prolonged transition affecting nearly every region of space. Determining exactly when this process occurred has become one of modern cosmology's most important goals. Independent observations, including measurements of the cosmic microwave background and absorption features in the spectra of distant quasars, indicate that reionization was largely complete within the universe's first billion years. Although significant uncertainty remains regarding its detailed timeline and the relative contributions of different sources. That uncertainty is where Webb enters the story. If early galaxies were more numerous than expected, if they formed stars more efficiently, if they produced unusually intense ultraviolet radiation, then they may have driven reionization faster than previous models predicted. The same galaxies creating tension in formation models might also help explain one of the largest phase changes in cosmic history. At first, that sounds reassuring. Perhaps one mystery solves another. But science rarely offers such clean resolutions. Because increasing the efficiency of early star formation creates new demands elsewhere in the models. Where did so much cold gas originate? Why did it collapse so efficiently? Why did feedback from exploding stars fail to suppress additional star formation as strongly as many simulations predicted? Every proposed solution answers one question while generating another. This pattern repeats throughout the Webb era. Measurements improve, models adapt, unexpected consequences emerge. One striking example involves chemical enrichment. The earliest stars should have formed from almost pristine hydrogen and helium. Heavy elements such as carbon, oxygen, silicon, and not yet exist in significant quantities. Those elements had to be manufactured inside stars and dispersed through stellar explosions before later generations could incorporate them. Yet several distant galaxies already display evidence consistent with surprisingly evolved stellar populations and significant chemical processing. Interpreting those observations is difficult. Spectral signatures become increasingly challenging to analyze at extreme distances, and multiple physical processes can produce similar observational features. Still, if even part of the apparent enrichment is confirmed, then stellar evolution during the universe's first few 100 million years may have proceeded with remarkable speed. That possibility forces astronomers to reconsider assumptions that once seemed comfortably established, not because the laws of physics necessarily changed, because familiar laws can behave differently under unfamiliar conditions. Think of water. Its chemical formula remains constant whether it appears as ice, liquid, or vapor. Yet identical molecules produce entirely different behavior depending on pressure and temperature. The same principle applies across astrophysics. Gravity has not changed. Nuclear fusion has not changed. Electromagnetism has not changed. But the environment of the infant universe differed profoundly from the mature cosmos surrounding the Milky Way today. Small differences in initial conditions can produce large differences in evolutionary pathways. That realization has shifted the conversation. The earliest Webb discoveries were often framed as a contest between two possibilities. Either modern cosmology survives, or modern cosmology collapses. Increasingly, researchers see a third option. The underlying framework may remain broadly correct, while important details governing the first generation of galaxies require substantial revision. History offers many examples of that outcome. Newton's laws remained extraordinarily successful, even after Einstein revealed circumstances where they no longer provided complete descriptions. Quantum mechanics expanded physics without erasing classical mechanics from everyday life. Scientific revolutions are often less about replacing everything than about discovering where previous approximations stop being sufficient. Whether Webb is exposing such boundary remains uncertain. But the telescope has already accomplished something equally significant. It has revealed that the earliest chapters of cosmic history contain more complexity than many investigators anticipated. And that complexity extends beyond galaxies. Because hidden behind every image lies another component of the universe that Webb cannot observe directly. The substance responsible for shaping nearly all large-scale cosmic structure. Dark matter. If the earliest galaxies truly assembled faster than expected, then questions about invisible matter become impossible to avoid. The investigation is about to move away from what Webb sees toward what it cannot. Dark matter occupies an unusual position in modern science. Nearly every successful model of cosmic structure depends on it. No laboratory has confirmed what it is. That sounds contradictory, but the contradiction is only apparent. Astronomers did not invent dark matter to explain distant galaxies discovered by the James Webb Space Telescope. The idea emerged decades earlier from completely different observations. Galaxies rotated too quickly for their visible stars and gas to provide enough gravity. Clusters of galaxies remained gravitationally bound despite containing far too little ordinary matter. Even the bending of light around massive structures consistently pointed toward far more mass than telescopes could see. Each measurement carried its own uncertainties. Together, they formed a remarkably consistent picture. Whatever dark matter is, it appears to outweigh ordinary matter by roughly 5-to-1. The universe we can directly observe is not the dominant component of its own structure. That invisible framework becomes especially important when discussing the first galaxies. According to the standard cosmological model, dark matter began clumping long before ordinary gas could efficiently form stars. Those invisible halos acted like gravitational scaffolding. Hydrogen and helium fell inward, eventually becoming dense enough for stellar ignition. Without those halos, galaxies would have struggled to assemble within the available time. Dark matter did not shine. It prepared the stage. If Webb is finding galaxies that formed more rapidly than expected, One possible explanation is not that galaxies themselves behave differently, but that the earliest dark matter halos assembled sooner or grew more efficiently than many simulations predicted. That possibility immediately raises another question. Have the simulations underestimated ordinary astrophysical processes? Or have they misunderstood something about dark matter itself? Researchers have explored both possibilities. The simplest version of dark matter is known as cold dark matter. In this picture, the particles move relatively slowly compared with the speed of light during the era when galaxies begin forming. Slow-moving particles clump efficiently under gravity, producing numerous small structures that gradually merge into larger ones. This framework has achieved extraordinary success across many independent observations. It reproduces the large-scale distribution of galaxies. It matches measurements of the cosmic microwave background. It successfully predicts many statistical properties of the expanding universe. That success is one reason cosmologists remain cautious about declaring a crisis. Changing dark matter is not a small adjustment. It affects nearly everything. Still, success on large scales does not guarantee perfection on smaller ones. Alternative ideas have existed for years. Warm dark matter proposes particles with slightly higher velocities in the early universe, suppressing the formation of the smallest structures. Self-interacting dark matter allows particles to collide with one another under specific conditions, subtly changing the internal evolution of galactic halos. Other models introduce ultralight particles whose quantum behavior could influence structure on astrophysical scales. None of these ideas emerged because of Webb. They were already being investigated to address other open questions. Webb simply provides another place to test them. So far, none has emerged as the clear explanation for the earliest galaxies. In fact, many researchers argue that altering dark matter alone cannot easily reproduce the observations without creating tension elsewhere. A solution that improves one corner of cosmology must not damage another. That balancing act defines much of theoretical astrophysics. Imagine adjusting the tension in one string of an intricate web. The immediate section may straighten. Elsewhere, another part begins to sag. The universe behaves similarly. Every successful model must satisfy constraints from galaxy clustering, gravitational lensing, supernova observations, nucleosynthesis, the microwave background, and dozens of additional measurements gathered over decades. An explanation cannot succeed by solving only the newest puzzle. It must remain compatible with the older ones as well. This is why scientific revolutions are often slower than public expectations. Extraordinary observations do not automatically replace established frameworks. They force every competing explanation to survive increasingly demanding tests. Meanwhile, Webb continues collecting data. Each observing cycle adds new galaxies. Some reinforce earlier conclusions. Others soften them. The statistical picture becomes clearer with every confirmed measurement. One important trend has already emerged. Instead of focusing on a handful of spectacular objects, astronomers are beginning to study entire populations of early galaxies. Large samples reduce the influence of unusual outliers and allow researchers to compare observations against simulations in a far more rigorous way. The question is shifting once again, not whether one extraordinary galaxy exists, but whether an entire generation of galaxies consistently differs from expectation. That distinction matters enormously. Nature occasionally produces rare exceptions. Changing fundamental theory requires patterns, not anecdotes. As the evidence accumulates, another realization becomes increasingly difficult to ignore. The challenge posed by Webb may not lie within any single discovery. It may emerge from the collective weight of hundreds of observations that individually seem manageable, but together begin pulling against familiar assumptions. Science has encountered this pattern before. Tiny discrepancies in Mercury's orbit eventually contributed to general relativity. minute irregularities in starlight revealed the expansion of the universe. Small deviations in galactic rotation led to the modern concept of dark matter. Each anomaly appeared modest when viewed alone. Only later did their shared direction become obvious. No one yet knows whether Webb's growing catalog represents another turning point of that kind. But if it does, the consequences will extend well beyond galaxy formation, because every estimate of the universe's history depends on one deeper assumption: that we understand the universe's opening conditions well enough to reconstruct everything that followed. The most unsettling possibility is not that the first galaxies formed too early. It is that they may be exposing assumptions embedded near the very beginning of the cosmic story. Assumptions that have remained almost invisible, precisely because they worked so well for so long. There is a temptation whenever science encounters an anomaly. If the measurements appear inconsistent with the accepted picture, then perhaps the accepted picture is wrong. History encourages that instinct. It is difficult to discuss astronomy without remembering moments when established ideas gave way to something larger. Earth was not the center of the solar system. The Milky Way was not the entire universe. Space itself was not static. Those changes happened, but they happened far less often than people remember. Most apparent crises disappear. Measurements improve. Hidden assumptions are corrected. Instrumental effects become understood. The theory survives, though usually in a more refined form. That historical perspective is why many astronomers have responded to Webb's discoveries with something that may sound surprisingly unexciting.
Patience.
Not because the observations are unimportant. They deserve equally extraordinary scrutiny. One lesson has already emerged from the first years of Webb science. The telescope is revealing an early universe that is more efficient, more active, and more diverse than previous observations suggested. That conclusion no longer depends on a single spectacular galaxy. It is supported by a steadily expanding population of distant objects observed across multiple research programs. The debate now concerns degree rather than existence. How much more efficient? How much earlier? How much tension is genuinely present? Answering those questions requires far more than collecting beautiful images. Every candidate galaxy must be analyzed repeatedly. Distances must be confirmed spectroscopically whenever possible. Stellar populations must be modeled using different assumptions. Dust properties must be estimated. Possible black hole activity must be separated from ordinary starlight. Independent research groups must reproduce one another's conclusions. Only after that process can a surprising observation begin to reshape a scientific framework. This slow progression is not a weakness. It is one of the reasons cosmology has become remarkably reliable. The universe is under no obligation to provide convenient evidence. Researchers compensate by demanding increasingly difficult tests before accepting increasingly important claims. Meanwhile, theorists continue exploring possible revisions. Some propose changes in how gas cooled inside the earliest halos. Others investigate whether intense bursts of star formation occurred more frequently than simulations assumed. Still, others examine whether feedback from supernova explosions behaved differently in nearly pristine environments with extremely low metallicity. Each proposal attempts to preserve as much verified physics as possible while explaining the observations Webb continues to deliver. There is another possibility that receives less public attention because it lacks dramatic headlines. Several small effects may be acting simultaneously. No single assumption may be wrong enough to explain everything. Instead, slight revisions to stellar evolution, dust physics, black hole growth, star formation efficiency, and numerical simulations could collectively account for much of the remaining tension. Science often progresses through accumulation rather than replacement. One correction rarely changes an entire discipline. Many modest corrections sometimes do. That possibility is harder to summarize in a headline. It is also consistent with how modern astronomy has advanced for decades. Yet, even if every current discrepancy eventually finds an explanation within existing cosmology, Webb has already accomplished something more enduring. It has expanded the frontier where uncertainty begins. For years, discussions about the infant universe depended heavily on indirect evidence and sophisticated simulations. Now, those earliest epochs are becoming observable, not perfectly, not completely, but directly enough that theoretical assumptions can no longer remain comfortably untested. Every new observing cycle extends that frontier. Every confirmed galaxy removes another region where speculation once substituted for evidence. Ironically, greater observational power has not simplified the universe. It has made its earliest history more intricate. That may be the deepest lesson Webb has offered. Progress in science rarely eliminates mystery. It relocates it. Questions that once seemed philosophical become measurable. Questions that once seemed settled become conditional. The boundary between confidence and uncertainty shifts, and it almost always shifts farther than expected. Perhaps that is why the earliest galaxies matter even to people who will never analyze infrared spectra or write cosmological simulations. They expose something fundamental about human knowledge. We tend to imagine understanding as a steadily expanding circle. Each discovery fills another empty space. Reality appears less accommodating. Every expansion of that circle also lengthens its boundary. The more we know, the more places exist where the unknown pushes directly against the known. The James Webb Space Telescope has enlarged that boundary dramatically. It has not shown that cosmology failed. It has shown exactly where cosmology must now work harder. That distinction may sound subtle. It is anything but. Because the strongest scientific theories are not those that avoid difficult observations. They are the ones willing to confront them. And few regions of modern astronomy now demand more careful confrontation than the universe's first few 100 million years. Those distant galaxies are not merely ancient collections of stars. They are records of conditions that no experiment on Earth can reproduce. Each photon carries evidence from a time when the universe itself was still deciding what kind of cosmos it would become. We are only beginning to learn how to read that record, and every successful interpretation forces another question into view. If our reconstruction of the universe's earliest history continues to evolve, how certain can we be about the story we tell from its very beginning? There is a familiar image that appears in books, documentaries, and classrooms whenever the history of the universe is explained. It begins with the Big Bang. Then a timeline stretches forward through billions of years. The first stars appear. Galaxies grow. Heavy elements accumulate. Planets form. Eventually, somewhere inside an ordinary spiral galaxy, observers begin asking how the story unfolded. The illustration suggests certainty. The reality is more cautious. Every segment of that timeline is reconstructed from evidence that has survived extraordinary distances, immense stretches of time, and layers of interpretation. None of those observations speaks for itself. Every measurement becomes meaningful only after passing through models that connect light to physical processes. That has always been true. What Webb has changed is the precision with which those models can now be tested. For decades, the earliest few 100 million years after the Big Bang were largely a theoretical landscape. Simulations explored possibilities. Observations provided broad constraints. Much of the discussion concerned what should have happened. Now the conversation increasingly concerns what appears to have happened. That difference transforms the scientific process. Instead of asking whether a simulation looks plausible, astronomers can compare it directly against galaxies whose light began its journey before the Milky Way even existed. Some comparisons agree remarkably well. Others refuse to fit comfortably. Neither outcome is disappointing. Agreement strengthens confidence. Disagreement reveals where new understanding is possible. There is another reason these observations matter. Cosmology is unusual among the sciences because controlled experiments are impossible. No laboratory can create another universe with slightly different initial conditions. No researcher can repeat the first billion years while changing a single physical parameter. The universe offers only one history. Astronomers must reconstruct it from the evidence that remains. That limitation makes every independent source of information extraordinarily valuable. The cosmic microwave background describes conditions roughly 380,000 years after the Big Bang. Large-scale galaxy surveys reveal the mature universe. Supernovae trace cosmic expansion. Gravitational lensing maps unseen mass. Now Webb is filling a region that was previously represented far more by prediction than direct observation. The overlap between these windows is where modern cosmology becomes strongest, or where hidden inconsistencies become visible. It is tempting to imagine that one decisive observation will resettle every remaining question. Each generation of instruments has solved problems that once appeared insurmountable, while simultaneously uncovering entirely new ones. The Hubble Space Telescope refined the expansion rate of the universe, but deepened questions surrounding dark energy. Precision measurements of the cosmic microwave background confirmed major aspects of the standard cosmological model while sharpening tensions over the present-day expansion rate. Webb is following that same pattern. Its greatest discoveries may ultimately be the questions it forces scientists to ask more carefully. Perhaps future observations will demonstrate that early star formation was simply more efficient than previous models assumed. Perhaps improved simulations will reproduce today's apparent anomalies without altering fundamental cosmology. Perhaps entirely new physical processes, still consistent with established laws, will emerge from decades of additional analysis. Or perhaps one assumption buried deep within our current framework will eventually prove less universal than it appears today. At this point, the evidence does not justify choosing among those possibilities with certainty. Scientific restraint is not hesitation. It is recognition that confidence should expand only as fast as the evidence allows. That restraint becomes especially important whenever observations touch the origin of the universe itself. Few subjects attract stronger public fascination. Few are more vulnerable to exaggerated conclusions. The earliest galaxies are not evidence that everything we know is wrong. Neither are they proof that everything we know is complete. They occupy the narrow space where discovery usually begins, between confidence and revision. If there is an unsettling implication in Webb's observations, it does not come from the possibility that cosmology has failed. It comes from something quieter. For generations, humanity has assumed that improving our instruments would steadily reduce uncertainty. Instead, every major advance has revealed that uncertainty possesses its own structure. As our view becomes sharper, the universe does not simply surrender answers. It reveals finer questions. The galaxies Webb observes have remained unchanged for more than 13 billion years. Only our ability to see them has changed. And with each improvement in that vision, the earliest chapters of cosmic history become less like a completed story and more like an investigation that had barely begun before we convinced ourselves we already understood the opening pages. Perhaps that is the enduring lesson of the James Webb Space Telescope. Not that the universe has become more mysterious, but that our confidence has finally reached the point where its hidden assumptions can no longer remain invisible. The farther we extend our vision toward the beginning of time, the less we are reminded of how much the universe remembers. The more we are reminded of how much we have yet to understand.